So, hello and welcome to another video from sickmaths.co.uk, where you can find the whole of GCSE Maths explained on video, all for free. So, this video is about vectors, and vectors simply get you from one place to another. Like this vector A, okay, is getting me from here to there. It's sending me 2 to the right and 3 up, and this vector B is sending me 2 to the left and 2 up, like it says over here. Okay, and this video about vectors is actually about combining vectors together. So if I wanted to combine this journey A and B together, I get this journey. Okay, and you can actually calculate these journeys by adding the vectors together. So if I add these two vectors together, I do 2 plus minus 2, I get 0, which is not surprising because I've gone 2 to the right and then 2 left. So basically haven't moved in the horizontal direction or the x direction. And I've gone 3 up in vector A and 2 up in vector B. So overall I've gone 5 upwards. Okay, so you can see the direct journey is like this, 0 across and 5 up. And that is the result of what you get when you do A plus B. So, the whole point of this little example in 1 is not to show you a typical question, because these kind of questions don't really come up when you've got the actual numbers. What it's supposed to demonstrate actually is that you can add vectors. And also, some people get confused. They see this from here to there is supposed to be equal to A plus B, but this looks really short compared to this. But actually, when you add the vectors, it cancels itself out and actually gives you the shortest result. So hopefully you won't be confused later on when we use this idea that something like this can be equal to that. Okay, so that was the main point of that just to make you confident that you can add vectors like that. So let's jump ahead now. So I want to actually define vectors again in the way where you don't use numbers, because most of these questions don't use numbers. And so if I'm defining vectors again, what I'd like to say is a vector has a certain direction and it has a certain size. Okay, so you can't, it doesn't mean, a vector doesn't mean go on forever or as long as you feel like in a certain direction. It's a fixed size. So you can see from here to there I need 2 A's. I can't just use 1 A, which is 1 A from O to N, just like we say over here. There's also some tiny other things I need to explain. For example, bold letters means vectors when you do it in print, as in what you'll see in your maths exam paper, GCSE Maths exam paper. It's printed by a computer, right? So that's what I mean by print. In print, a vector is denoted by a bold letter, okay, but by handwriting, by hand, you normally just write it normally with a little tilde underneath, and that denotes a vector. So this vector A is actually the same as that vector, but that's supposed to be like in print, but that's me actually trying to scribble it and making it darker. But anyway, and what else is there to explain? This O to N with this arrow here just means I want to get from O to N. That's all it means, yeah? But whenever you're defining how to get from one place to another, you have to use your little vectors, okay? All the answers have to be, in this case for this picture, all in terms of A and B. So, from O to N is simply A. That's it, easy. O to X is equal to B. That's very easy to see, O to X. You can see an arrow, by the way, also. That gives you the direction it's going in. If you go opposite to that direction, you have to do minus. So, for example, N to O is equal to minus A. Now I really should stick to this plan here. So O to N we've done, O to X we've done, O to A. O to A is equal to 2A. It's quite easy to see that's equal to 2A. A there, and then another A to get to A over there. What else is there? A to O. A to O is going in the opposite direction of what we just did. So O to A was 2A. A to O is minus 2A because it's going in the opposite direction of the arrows. What's next? done A to O, A to B, A to B. Now this is kind of plugging in back to what we just did earlier on over there. A to B, we can't go directly because there aren't any vectors there, so we go this way. That's minus 2A plus 2B. So this vector from there to there is equal to minus 2A plus 2B. And that shouldn't surprise you, because I told you that when you add the vectors, they sort of cancel each other out and do equal that shortest route. Okay, where are we now? Oh, we want to work out A to M, which kind of helps because we just worked out A to B, right? So working out A to M is not going to be difficult. And just by the way, M is the midpoint of A to B. So A to M is half of what A to B was equal to. So A to B was equal to minus 2A plus 2B, like it says there. So A to M is half of A to B. So half of A to B is minus A plus B, and that's it. Where are we now? So we got that A to M covered. G, N to M, N to M, from there to there. Well, we just worked out A to M, which was minus A plus B. Notice how the previous question helps with the next question. That's quite normal even in a GCSE exam. Not always. When they want to make it difficult, they might not help you out so much. But often, part A of a question might say work out A to B, then part B might ask you work out A to M if they're trying to make it easy for you. Sometimes, not always. Okay. Anyway, so N to M we can work out really easily because we just worked out A to M, which was minus A plus B. And N to A we know is A. So altogether we have to do A plus minus A plus B. As I've written here, A plus minus A plus B. NM is that. And then A minus A plus minus A is nothing, so you're left with B. And that's it, that's the answer. N to M is equal to vector B. Now, we're going to show NM and OB are parallel. We're going to show NM and OB are parallel, i.e. they'll never touch. They're in the same direction, sort of thing. So NM is equal to B, just to recap, and OB is equal to 2B. So that's equal to B, that's equal to 2B. They are both multiples of B, okay, which basically means they're made of the same vector, but just different amounts. This is one of them, and this is two of them. Now, a vector has a fixed direction, so it doesn't matter how far you go in that direction, the two lines will be parallel. They won't be as long as each other, but they will be parallel because they will have the same direction, because they're composed of the same vector. They're multiples of vector B. So they have the same sort of slope, you might say, or same direction, and therefore they are parallel. Those three dots mean therefore. Okay? So that's covered. Let's quickly go on to the next one. ABCE, this thing here, is a parallelogram, and also another useful bit of information, DE is equal to 2CD. So this is twice the size of that. Or, as you'll see in a minute, another way of looking at it is there's a line, and this is 1/3 of the line, that's 2/3 of the line. Now, parallelograms are very important because if you have two parallel sides which are the same length, they're basically the same vector. So this vector is the same as that vector, like you'll see here. C to B is equal to N. B to C, going the opposite direction, is minus N. Okay? C to D, well, we said that's 1/3 of this line. Now, this line from here to there is minus M. So this from here to there is minus 1/3 M, this thing here. Okay? Because this is parallel to that, and it's the same length. This is equal to, from here to there is M, so the opposite direction is minus M, well, we've only got 1/3. I'm just kind of repeating what I just said earlier on. So minus 1/3 M from there to there. C to D. That's covered. B to D. B to D is equal to that plus that. So that's minus N plus, what do we say? That was minus 1/3 M. Okay, so minus N plus minus 1/3 M, or just simply minus N minus 1/3 N. M. Okay, so there you go. D to F, from there to there, is minus 2/3 M minus 2N. Like it says here, except for I swapped it around so you can compare these two easily. I put the N's first and I put the M's afterwards. Don't have to do it that way. But you can see this thing is twice this thing here. Double that to give you minus 2N, double this to give you minus 2/3 M. So, What have we got to say now? We've worked out this, and we were talking about how this thing is double that one, which will come in use in a minute. Show that BDF is a straight line. So BDF is a straight line. Well, you know how we showed two things are parallel if they compose or they're multiples of the same vectors, or multiples of the same compound vectors, I might call them even sometimes. Okay, that means they have the same direction, and in this case they were parallel. But in this case, since they're touching each other, they can't be parallel, but they can make a same straight line. So that's what we're going to show. We're going to show them multiples of the same vector, so they are basically in the same direction, therefore they are parallel. Okay, so let's show that B, D, and DF are multiples of this vector. That's what we were talking about earlier on. This is twice that. So basically they're both multiples of this complex or compound vector minus n minus 1/3 m. So that's minus n minus 1/3 m, and there's double that. So there definitely are multiples of the same vector, and therefore they're parallel. Let's quickly finish off over here. A very tiny example. Basically, you've got equilateral triangles. They're spelled in a strange way with an apostrophe, so missing out the E-R-A. So equilateral triangles. And why do we care that they're equilateral triangles? Because equilateral triangles together make parallelograms. Remember how parallelograms were useful? I could work out lengths that are not labeled. So the same way, these create parallelograms, because equilateral triangles have 60, 60, 60 in each corner. These two 60s make 120, and that's 60. Therefore, basically, those this line and this line are parallel. I could explain that in some more detail, I suppose. If I continue that line, I would have had an angle there. This line here, I would have had an angle here that was equal to 60. And basically, if that's the situation, you can see those lines must be those angles are corresponding. Therefore, these two lines must be parallel, basically. What else is there? So basically, that's all I want to say is if this creates a parallelogram, then therefore y to z is equal to vector q, since this is already vector q. And that's all I need to say really about